Hi folks, welcome to the first of three little videos just looking at the last three lessons of circles. This first one, as you can see, is on how lines and circles intersect. We're going to see some similarities here to quadratics and how lines and parabolas intersect, some of the same skills involved, and some of the same criteria, looking a little bit at the discriminant as well. Okay, so let's get started. So in this first slide, and again, you can pause the video and copy this into your notes. In this first slide, what we're looking at is that there's really only three ways in which a line can interact with a circle. In the first diagram over here, we've got where the line intersects at two points of contact here, and the discriminant for that, same as with quadratics, would be greater than 0. We've then got the middle diagram, this one here, looking at when the line meets the circle at just one repeated point, and we would call that like one point of contact. And that line then, so this line here, is then called a tangent. So this is tangency in the same way that a line could be a tangent to a parabola. We've got the same thing happening with circles, and tangents to circles, quite a big idea that we'll look at both this lesson and next lesson. And then we've got the final diagram over here on the right, where we've got that the line just doesn't interact with the circle at all. So there are no points of contact, no points of intersection at all, and the discriminant there would be less than 0. And you might be thinking, like, how do I use the discriminant? Because the equation of a circle, has both x squared and y squared and x and y and stuff involved with it. I'm only used to seeing the discriminant whenever I'm dealing with a quadratic. So we're going to look at a wee example just to see how the discriminant applies. Okay, so example 1. We're going to be showing that the line y equals x plus 6 is a tangent to the circle. So this is a show that question, which means that we are essentially trying to prove that it's a tangent, and we've got a couple of ways that we can do that. We saw them both when we were dealing with quadratics. The first way is to use a discriminant, and again we'll look at how we can apply a discriminant to this example. Or the second method is to actually find the points of contact and show that there is in fact only one. I'm going to use the discriminant method for this example because we're going to look at two further examples where we actually go ahead and find the points of contact. You can pretty much for all cases use just finding the points of contact for all of them. But like quadratics, there might be an example where, there is an unknown in place of one of these coefficients. It could be like minus by or something like that, and you've got to find b. And in that case, it might tell you the line is a tangent, and that would give you additional information that would allow you to do that. But if it's a show that question, you've got a choice, you can use either. But like I say, I'm going to use the discriminant approach for this. But like I said, how to apply the discriminant to this? Well, the first thing we're going to do, and we're going to be doing this whenever we try and find the points of intersection as well, is we're trying to almost like solve this simultaneously. But we can't do elimination in the same way we could with two lines. We can't even do like y equals y, which was what we were doing when we had a line and a curve. And so we kind of need to rely on our third approach for solving this type of equation, which is substitution. So we're going to take the line, which is y equals x plus 6, so this equation here, and what we're going to be doing is we're going to be substituting for y in the circle equation, so we're going to be taking the y values, there's two of them, you can see them both there, and we're going to be replacing y with what y is equal to if the line and the circle meet, which is that y at those points will be equal to x plus 6. So let's go ahead and do that and see what that looks like. We've got x squared plus, and then we're replacing y here with x plus 6, all squared, plus 2x minus 2 lots of, and again we hit another y here, so we're replacing all y's with x plus 6, and we've got a minus 6 on the end here, and that's all equal to 0. Okay, we're going to break the brackets now and collect like terms. I'm going to square out the brackets quickly. If you need to, you can write them as x plus 6 times x plus 6 and multiply them out that way. If you don't, if you're not quite comfortable with how to square out brackets quickly, but I'm going to just square the first term. I'm going to multiply the two terms and double, so I get 12x in there, and then I'm adding 36 from the end. I've got my 2x just watch out for this. We're thinking about it like -2 multiplying out the bracket, so that's going to be minus 2x minus 12 minus 6 on the end there. Okay, we're going to collect like terms. So we've got a couple of x squared terms there, so that's going to give us 2x squares. We've got 12x, add 2x, take away 2x, so that's just going to leave us with positive 12x. Yep, and then we've got 36, take away 12, which is 24, and take away another 6, which is 18. So we've got positive 18 on the end here as well. Okay, this is just an equation. It now looks like a quadratic, which is great, and we can see how we could apply the discriminant to this now. But what we're going to do is I'm just going to divide through by 2 just to get things as simple as possible before I do anything additional with them. And I get this. And we've done quite a lot of work on perfect squares, and some of you will just instantly recognise this as a perfect square. It would factorise to x plus 3 all squared, and that way you could find the points of contact fairly quickly and prove that it's a tangent that way. But just so that we've got a wee example where we're using discriminant, I'm going to go ahead and use that approach. So to use the discriminant, we have to get our a, b and c values. So we've got the a is equal to 1, that's the coefficient of x squared. We've got b is equal to positive 6, the coefficient of x, and then we've got c is equal to positive 9. I'm just going to come over to the left here to evaluate this, so I'll just do it in this little box over here. And we've got the discriminant, b squared minus 4ac. Now this isn't equal to anything at the moment. We are trying to show that it's a tangent, so we're not making it equal to 0 or greater than 0 or less than 0. We are evaluating it, and we should get a result of 0. And that would convince us that the line was a tangent to the curve. So we've got 6 squared minus 4 lots of 1 times 9. And we can see that's going to give us 36. Subtract 36. And that is going to result in this value of 0. We do need a little statement just to kind of confirm that this discriminant does show that it's a tangent. And so we're going to write as b squared minus 4ac equals 0. There is 1 point of contact, and therefore the line is a tangent. Gonna have to squeeze us into the circle. Okay. All right, so what we've seen in this example is how we're going to consider how a line and a circle interact, and we're going to do that by substitution. Whilst we substituted in for y in this case, if you were given a line where x was the subject, then I would substitute in for x, and the same logic applies. Also, if you are given a line equation that's not in a form of y equals or x equals, then you can just rearrange it into one of those forms, and I would just go with whichever one you think is simplest. Okay, so that's our first wee example of how a line and a circle interact, and in this case we're showing the line as a tangent to the curve. Okay, example 2. What we're going to do this time is we are going to find the points of intersection, but we're going to see a lot of similar skills going on here. We're going to be starting by substituting in the line, y equals 2x, and we're going to be substituting in for y again because, we've got the line in the form y equals, so we can replace y easily. What I was saying in the previous slide is we could essentially like half each side and get a half y is equal to x and replace all the x's with a half y. Yeah, so we could, we could take the x's and replace them with x equals a half y if we wanted, but why would I introduce something that's more complex in the form of fractions when I don't have to? Okay, so we're not going to go down that road. We are simply going to be substituting in 2x for every y that we see. Of course, our equation this time, in this form, we've got a circle where the centre is at the origin, so the equation of the circle looks a little bit simplified, and we'll do one where we've got the full equation in the general form in just a wee minute. Okay, so let's have a look at how this behaves then. So we've got x squared plus, and we're going to have y squared, but we're going to be replacing y with 2x. Careful with your brackets here, it's 2x all squared, and we'll see what difference that makes in a little second. If you don't have the brackets, of course, what you write is this, And what you should really have if you're squaring this is you've got to square that to the coefficient of x as well, and so we should have this. Yeah, so just watch out for that whenever you're substituting in there. Okay, collecting like terms gets us to this point here, and this is an interesting point to be at. I think naturally what we do is divide through by 5, and that leaves you here. Now, we've discussed examples like this in class quite a lot. We can, of course, just square root each side here, but in doing so, I think we're prone to making a mistake of missing the solution of -3. So I would like you just to consider this as a quadratic, so there's our x squared term equation, and generally we are going to try and solve quadratic equations through factorising. So we're going to subtract 9 from each side to get us to this form, and then we're going to factorise, and this is now a difference of 2 squares, and whenever we factorise we're never going to miss that second solution. So we've got x, and we've got 2 3's, 1 positive, 1 negative, and we can see that we're going to get our 2 solutions from here. We're going to apply the zero product rule, we're going to split and solve, and we get that x plus 3 equals 0 and x minus 3 equals 0. And this leaves us with x equal to -3 and x equal to positive 3. And those are our 2 x values. But we're looking for the points of intersection. So we're going to list these as coordinates, which means we need a y coordinate. To do that, we can take these x values and we can substitute them into either equation, either the line or the circle. We've got a couple of things we're going to think about here. The first one is which one's simpler, and I hope you would agree the line is definitely substantially simpler to substitute into. But unlike when we've done it with a curve or we've done it with another line, a circle isn't a function. And so we have a bit of a problem if we substitute back into the circle. Let me just try and highlight that for you. Here's my best go at a circle. That's not too bad. And what we've worked out is that there is an x coordinate at -3 and an x coordinate of 3 where these points of contact lie. Now, if we just consider the line really quickly, we've got y equals 2x, so that's a line with a positive gradient of 2. Let's say it looks something like this. We know we've got 2 points of contact, one here and one here, one at -3 and one at +3 in terms of the x coordinates. Yeah, so something like that. But what you can see is that those aren't only the y values that occur, or the only points that exist where x equals 3 and -3 on that circle. Yeah, there is another point here that exists when x is equal to 3, and there's another point up here that exists when x is equal to -3. And if we substitute back into the circle, we're going to get 2 answers, and then we've got to discern which of our answers is the correct one. Yeah, and so there's a whole bunch of unnecessary work in there. So rather than it just being a preference of substitute into the line or the circle, I want you to always substitute back into the equation of the line. You'll naturally gravitate towards that anyway because it is going to be simpler, but that's just a word of warning that you can get yourself in a bit of a pickle if you don't pick appropriately. Okay, so let's go back to our line, y equals 2x. And consider when x is equal to -3, what does this look like? It looks like this, y equals 2 lots of -3, and so we get y is equal to -6. And that means we've got 1 point of intersection at -3, -6. And we get a second one when x is equal to +3, and of course that's just y equals 2 lots of +3, so y is equal to +6. And again, that gives us our other point of intersection, 3, 6. So we've got 2 solutions to this problem. We've got when x is -3 and y is -6, and when x is 3 and y is 6. Those are our 2 points of intersection. Okay, on to the last example. We're just going to make this slightly trickier by looking at an example with the full general equation of a circle. Okay, we've got a slightly more complicated line this time, and that its y-intercept isn't at the origin, but the approach is still going to be exactly the same. We've got our line in terms of y, so we're going to be replacing y in the circle here and here. Cool. So we start with our circle equation, and anytime we see a y, we're going to replace it this time with 2x minus 4, and that first y is squared. we're taking away 2x, and then we're subtracting 6 lots of 2x minus 4. Again, we hit another y there, and then we've got the plus 5 on the end equal to 0. Okay, I'm going to square out the brackets quickly again here. So this is going to give us 4x squared minus 16x plus 16 minus 2x. And we're going to be subtracting this 12x and adding 24. Just watch out for that one. Plus the 5 equal to 0. Okay, collecting like terms, we get 5x squares. We've got negative 16x, and taking away another 14x gets me negative 30x. And then I've got 16 and 24 and 5 gives me 45 going on here. Okay, again, we can see we've got a factor of 5 here, so we're going to divide through by that to make life a wee bit simpler. And this time there's no danger of us kind of try to solve this any differently. We've got everything on the left, it's equal to 0. We're going to go ahead and factorise. This one's actually a perfect square as well, so our line is going to be a tangent. We get x minus 3, x minus 3. We're going to split and solve. And we get x minus 3 equals 0 and x equals 3 twice. Yeah, one from each of those. But it's a repeated point, so there's only one point of contact. We need to just find the y coordinate, and again, we just discussed we're going to go back to the line equation, so y equals 2x minus 4. We're going to consider this when x is equal to 3, and we get y equals 2 lots of 3 minus 4, and so y is equal to 2, giving us our point of contact of 3, 2. And like I said, because this is one repeated point, then this is a tangent. And I would be taking the approach of, using that method to prove that it's a tangent if it also asked me for the points of intersection. Even if it doesn't, you can still take that approach. But like I say, there might be a few kind of niche instances where the discriminant is appropriate. Okay, so that's your 3 examples. Here are a couple of exercises you can try from the book. These page numbers are actually from the first edition of the Heinemann Maths book, which is one we've been using in class. If you do have a newer copy, the second edition, then the pages will be, I think they're slightly further on in the textbook, about 221, 222, something along those lines. But you can obviously rewatch the video, make sure you've got those examples in your notes jotter, and then have a wee go at these questions. Just give your answers a mark from the back of the book when you are done. Okay, so just get in touch with me if you've got any problems, but hopefully that gets you up to speed with how lines and circles intersect.